This video is a stoichiometry video about limiting reactants specifically. Today's learning target is to learn how to calculate the percent yield from the limiting reactant using stoichiometric proportions in a balanced chemical reaction. So let's begin with the concept of limiting reactants. Limiting reactant is the reactant present in the smallest stoichiometric amount. In other words, it's the reactant you'll run out first. In this case that you see here, the example that you see down here, you'll notice that hydrogen will run out first. And so in order for us to know which one runs out first, you need to have the balance equations. For every 2 molecules of hydrogen, 1 molecule of oxygen reacts to form 2 molecules of water. This is on a micro scale, so we're looking at things on a micro scale. So I'm going to write that in, micro scale, okay? So on a micro scale, for every 2 molecules of hydrogen, you need 1 molecule of oxygen. So for every 2 molecules of hydrogen, so I'll group them here. Here's one grouping. You'll make 2 water molecules for every 2 hydrogen to every 1 oxygen. So let me group these 2. This will make another 2 water molecules. And then another grouping will give you another 2. And then here's one of the last groupings. So now you'll notice that you'll have an excess amount of oxygen. These 2 oxygen molecules are not consumed, and so there's an excess reactant. The one that's limiting, meaning the one that you don't have enough of, the one that ran out first, was hydrogen gas. So you don't have enough to accommodate for these 2 oxygen molecules. So oxygen in this scenario is the excess. So we call it the ER for short. And then hydrogen is the limiting reactant. So we call it the LR, okay, for short. So notice how many water molecules you can make. You can make 2 for every grouping, right? 2, 4, 6, 8, 10. So the max you can make are 10 water molecules. Take a count at it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And notice the 2 oxygen molecules that are in excess. Now, the excess is going to account for the law of conservation of mass, meaning however many water molecules plus the excess amount will then account for will be conserved from the reactant amounts, okay? So let's go ahead now that we understand what limiting reactants are, the hydrogen in this particular scenario being the limiting, and then the oxygen being the excess that doesn't react, okay? Okay, so we'll need, in order to calculate the percent yield, just as our targets stated, is to make sure that you know the equation. So it's an experimental yield over the theoretical yield. The theoretical yield is basically the stoichiometry. So you're doing stoichiometric proportions to figure out what you should form theoretically. The experimental yield is basically when you go in the lab and you do your experiment. So you actually go into the lab and you do an experiment. Upon doing the experiment, you yield a certain amount of your driving force, usually your driving force, which is your product. So it's as you see defined here, it's a comparison of the amount actually obtained in a laboratory experiment to the maximum amount it is possible to make from the stoichiometric proportions, as you see written out here. So that's the equation that you'll need to have. So we're doing 3 problems, and they'll take a while to go through each of those 3 problems. So make sure you have your periodic table out and you have your calculator out ready for you, okay? So to begin a problem, I first do a quick read through and see if we're looking at a stoichiometry problem. And so take a few minutes to read that through, pause it, and take a few minutes to read it through. You'll notice that you're looking at finding the mass of sodium chloride from the masses of chlorine and sodium that reacted. So this is a stoichiometry problem. You're looking at products, the amount of products from the amount of reactants. And all stoichiometry is making sure mass is conserved. So the law of conservation of mass is adhered to. So the first thing you want to do is write a reaction, and your reaction must be balanced. So I start off with sodium reacting with chlorine, and it forms sodium chloride. So I'll notice that chlorine is diatomic. That's why I wrote chlorine as Cl2. Now, upon balancing this, you'll notice 2 coefficient is necessary for the sodium chloride, which makes us have a 2 coefficient here. I'm going to put the 1 here so that I can see the mole ratio. The mole ratio, we're looking at macro scale, so the mole ratio is 2 moles of sodium for every 1 mole of chlorine to form 2 moles of sodium chloride. On a micro scale, it would be 2 atoms of sodium, 1 molecule of chlorine to form 2 formula units of sodium chloride. So that's how you read it on a micro scale. So let's go ahead and begin. Now notice you're given grams of both of your reactants. So you're given grams of these two. If you'd like to write it down, it's good to write it down right underneath so you can see what your starting point is and how to start this problem up. So it's nice to write it down so you can conceptually visualize how you're going to go about doing this problem. So notice you're given grams of both of these reactants, and you're asked to find the grams of your product from that. So to do this, you'd have to compare the ratio, but the ratio is all in moles, so you have to convert your grams to moles. So take a second and convert that, 2.922 grams of sodium, and you're going to convert it to moles. So 1 mole of sodium has 22.99 grams of sodium. Upon converting it to moles, then you can do a stoichiometric proportion with using this equation, which is a mole ratio. So you have 35.45 grams of chlorine, and you want to convert it to moles. Notice that chlorine is a diatomic molecule, so you must take the molar mass of both chlorines, so it's 70.9 grams of chlorine. So once you convert these to moles, and you notice that this number is pretty nice, it's a tenth, so you'll notice it's 0.100 moles of sodium, and this one's half, so it's half a mole. Okay, the number is really nice, so you can really focus on the concept of understanding limiting reactants in stoichiometry. So now you've got your moles of both your reactants. Now you can then compare it to the stoichiometric ratios. For every 2 moles of sodium, you'll need 1 mole of oxygen. So do you see a 2-to-1 ratio here? You don't. You see quite a bit of chlorine, don't you? You see 5 times more chlorine than sodium. Now, if you want to do it, if the ratio was really difficult, what you would do is you'd divide it by the molar value. So it's 2, and you'll notice you get a value of 0.05. You divide this by 1, because the molar value is 1, you'll notice that you'll get 0.5. So the lesser amount is the sodium, and so sodium is your limiting reactant. What I like to do is I like to put LR and circle it right above the number of that for that limiting reactant, so I know that's the amount that my starting point. Now I move through, and I can use my limiting reactant to be able to solve for sodium chloride. Now, notice you divide it by 2, so you've got to really make sure you ignore this part, okay? So now let's do a mole ratio between the limiting reactant and the product, because how much you can make of the product depends on the limiting reactant. And notice it's a 2-to-2 ratio, which is a 1 for every 1 mole of sodium chloride. There's 1 mole of sodium needed. So that's really nice. Now you're going to convert your moles of sodium chloride into mass. So find the molar mass of sodium chloride, and that's 58.44 grams of NaCl. And then you do your math, noticing the units canceling out really nicely, leading you to the mass, a mass value of 5.844 grams of sodium chloride. And I want to label this. I'm labeling it because it's really important for me to see what it is that I am solving for. And so this is my theoretical yield, or mass. You can say theoretical mass. I'm going to put it in parentheses, theoretical mass. Okay, so now here's my, that gives me my, the answer, the mass of the sodium chloride for that first part. Now it's asking me for the excess, and I know this is my excess. Now, how much of my limiting, or given 0.1 mole of my limiting, how much of my excess would react with all that limiting? And you should see a 2 to 1, so half of that amount. So whatever amount you have of your limiting, half that amount is how much of the chlorine will react. But how much do we have? Well, we have, according to what you see here, this is what we have. I'm going to erase this. This is what I have of the chlorine. Half of this amount is how much of the chlorine will react. What's half that amount? 0.050. 0. And so that's how much chlorine reacted. Well, how much is left over is just the difference between the two. Upon taking that difference, you'll see it's 0.4500, and then you can calculate the mass by doing a mole to gram conversion. It's 70.9 grams of chlorine for every 1 mole of chlorine. Okay, and then you will then get your mass of your excess chlorine. And so I'm going to write the word excess just to remind myself this is what I am calculating. And so the last part is to, so if you think about it, I've got this done, now I've got this done, now I need to figure out the percent yield. And it tells me if only this amount of sodium chloride, which is my driving force, were made in the laboratory experiment, what is the yield? Well, theoretically, I should form this amount. So this is the percent yield of sodium chloride, and experimentally, I should form this amount. So this is my experimental mass, this is my theoretical mass. I take a ratio of both, and I'll notice it's really a nice number. So this number, it's like 50%. And then multiply by 100 because I'm doing a percentage. And I'll notice a nice, perfect 50% yield, okay, of sodium chloride. So I'm always interested in labeling. And I box all my answers at the very tail end so that I can clearly show Mrs. No that you have the answers to these parts. Let's go to problem number 2. Problem number 2. Take a second and read problem number 2. Pause if you need to and try this problem on your own if you'd like to venture into trying these problems independently. So because chem is dry. So go ahead and pause it and start the problem on your own. I'm going to work the problem out right now. So starting off, I start off with the reaction, knowing that it's a limiting reactant problem after reading through it. And my reaction looks like this, where I'm taking, I'll need another sheet of paper. This is going to be a long problem probably, or I have not much room for it. So I've got nitrogen reacting with hydrogen to form ammonia, which is NH3. Okay, I balance out my equation, seeing that my coefficients need to be 1:3:2 mole ratio. And then I start off by writing out what I'm given. It's nice to write out what's given. So I have 56 grams here of nitrogen and 6.1 grams here. I'm asked to find how much in grams of my products and also my excess. So let's go ahead and begin. First things first, convert your grams to moles. it's 2 moles. Nice number. 2 moles of N2. And then you convert your other grams into moles. Grams of hydrogen into moles of hydrogen. And dividing that, I get 3 moles. So some of you can see the stoichiometric ratio really quickly right off the bat, and you can see who the limiting reactant is. Some of you need to divide it by the mole coefficients of each of the corresponding substances. If you divide this by 1, you get 2. You divide this by 3, you get 1. So it looks like this is going to, hydrogen is going to be my limiting reactant. So I'm going to say Lr. You don't need to divide unless you really can't see which one is the limiting reactant. So when the ratio is a 1 to 3, it oftentimes is easy to see it, who the limiting reactant is. So I'm going to take my limiting reactant and figure out my products, which is ammonia. So I'm going to have to do a mole ratio between the two. So for every 3 moles of hydrogen, there's 2 moles of ammonia produced. So then convert it to grams. Gram is the measuring unit in the lab, so that's why we like to convert it to grams. So using the molar mass of 1 mole of ammonia, we can convert however many moles into grams. And the final answer is 34 grams of ammonia. And again, I remind myself that this is my theoretical yield, okay? So I'm going to write down theoretical. So now I'm ready for my excess. My excess is right here. Here's my excess. I have 2 moles that I have of it. How many moles of my excess will react with my limiting though? So if I have 3 moles of this, you can look at it as 3 moles of this substance here. How many moles of my nitrogen would I need? Well, look at this. It fits the ratio really nicely, so you need 1 mole of your nitrogen. So you have 2 moles. So this is how much you have. You're going to subtract how much reacted. This is how much reacted. And that will then give you how much you have in excess. So it's 1 mole of nitrogen that is in excess. So then you convert your 1 mole of nitrogen into grams. And really 1 mole of nitrogen means it's the molar mass, because the molar mass is the mass in 1 mole of that substance. So in 1 mole of nitrogen, there's 28.02 grams of nitrogen. And so multiplying that out, you will get 28 grams. You got to sig fig it also. Okay? So this is my excess. Now we get into we're done with how much excess, how much mass of ammonia, done with that. And then we're now ready to do your yield. Percent yield of your driving force. Your driving force is ammonia. So percent yield of that. And so that would be equal to, you take your theoretical, which is on the bottom here. You should 34 grams of ammonia. And then you take your experimental. So it says a student performs this lab experiment and measures the mass of the ammonia to be 3.41 grams. So this is your experimental. That's the laboratory portion of it. Multiply by 100. Divide and then multiply by 100. You get a yield of 10. Because the sig figs, this is 2 sig figs. You should have 2 sig figs, so this is 10% yield of ammonia. Okay. Any questions? Hopefully you can ask in class. We're on to the 3rd problem. Oh, sorry. There's one more idea. It says, what could account for such a low yield from his or her experiment? Now, in this experiment, you're collecting a gas. Oftentimes, when you're trying to collect a gas, you have to be able to hold that gas into the container. So oftentimes, the gas will escape from the container And so you're going to see a significant loss of your gas, ammonia, as a result of this. Okay, so let's go to problem number 3. In problem number 3, we're looking at a different format or a problem that's a little different. I like being able to take a problem and kind of change the format. It's more of a table now. So this helps you to see what it is that we actually do in a laboratory when we do a limiting reactant experiment. Okay. So take a second, pause it if you need to read through the problem. I'll start the process of this problem. Start off with a reaction. I have to have a balanced chemical reaction for potassium sulfate and barium nitrate. So I'll set up the reaction for this. Potassium sulfate is K2SO4, and it's going to react with barium nitrate. It's going to form, well, if you look at this reaction, it is a double replacement reaction. And in any double replacement reaction, we're looking at usually a driving force of a precipitate, usually, not always. Sometimes we form a molecular species that's like a weak acid. Most times you're looking at a precipitate. So here's my precipitate right here. Here's my driving force. Balance this equation out. This is a lovely ratio. That's the other thing about these reactions. Sometimes they produce really lovely ratios. So according to the original problem, you're looking for the theoretical mass of the precipitate formed from the reaction, given 1 point. So let me write down the given under here. So you're given 1.74 grams of this substance and 5.23 grams of this substance, barium nitrate, and you're asked to find the precipitate. And we identified the precipitate is barium sulfate, and we're looking for grams of that. So the first step is to convert your grams into moles. Make sure you write neutral compounds as you're setting up these reactions as well as these problems. Okay, so I'm going to convert my grams to moles. So 1 mole of K2SO4 has a mass, molar mass of 174.27 grams. Same here, 1 mole of barium nitrate has a mass of 261.35 grams. Again, a very nice mole ratio, just to remind you. When I divide these numbers, I get really small numbers, but it won't intimidate me. It's just really small. So this is moles of potassium sulfate. And then this one is 0.02200 moles of barium nitrate. Okay. So now it's a 1-to-1 ratio, mole ratio, which means the lesser amount, straight out, the lesser amount is going to be the one that's limiting. So the lesser amount is right here. So here's my LR, circle it just to remind myself. I'm going to use my LR to get to my products. What's the mole ratio between the potassium sulfate and the barium sulfate? So it's a 1-to-1 ratio, lovely ratio. So for every 1 mole of potassium sulfate, there's 1 mole of barium sulfate. And then you convert it all the way to mass. So the molar mass is 233.4 grams for every 1 mole of barium sulfate. Running out of room. And then you multiply and divide and do your math, and you'll get an answer of 2.33 grams of barium sulfate. And once again, This is your theoretical, because you went through the stoichiometry to figure out how much you should theoretically form from this reaction. So this is your theoretical mass. So now we go to your excess. Your excess is right here. If this is your limiting, this must be your excess. So barium nitrate is your excess. To figure out how much, you currently have this amount, right? So to figure out how much reacted, you have to figure out from your limiting how many moles reacted with your limiting. So if you have 0.00998 moles of the potassium sulfate, that same amount is going to be how much reacts with the potassium sulfate. So the same, they're 1 to 1. So you're going to subtract that number, 0.00998 moles, because that's how much reacted of the barium nitrate. Okay, and subtracting those two numbers, you get this number. These are not very nice numbers, but you've got this lovely handy calculator to work through the problems, to help you work through the problems. So 1 mole of the barium nitrate has a mass of 261.35 grams. And then that will give you the mass, so that will equal 3.14 grams of barium nitrate. Now we are ready for the yield. So we're on part C. This is A, B, and C. So the yield of the precipitate. So the precipitate is the barium sulfate. So theoretically, you should form 2.33 grams of barium sulfate. But then you actually, if you go back to the problem, this data table will tell you how much you actually form. So it's the one with the precipitate, right? So here's your filter paper. Let's imagine what's happening. So you mix your two solutions into this beaker and you see a precipitate forming. That precipitate then is filtered through a filter paper that's put into a funnel, and so it'll be removed from this solution by the filter paper, and then all the other filtrate gets passes through. Most of it is water and your spectator ions. So you're then left with a filter paper that's dried. Hopefully you leave it over a couple of days to dry it, and you'll see that to get the amount of the precipitate is to subtract those two values. So subtracting those two values, you then get the mass of your precipitate. So when I subtract those two values from each other, my mass of my precipitate ends up being 1.80 grams. So that gives us your experimental mass. So this is your, what is called your experimental mass, okay? And to do your percent yield, you just take your experimental over your theoretical of the precipitate, and you'll see that it's 77.25% of my barium sulfate. Again, I'd like to box these answers out at the end just to make sure that these are where the answers are, okay?